Welcome to the tutorial Querying in the Age of Graph Databases and Knowledge Graph. My name is Marcelo Arenas, and I will be giving this talk with Claudio Gutierrez and Juan Sequeira. Let me start by giving you a brief overview of this talk, what we have called here a conceptual map of this talk. The motivating question for this tutorial is why the boom? Why today we are talking so much about knowledge graph and graph databases? To try to give an answer to this question, we consider three different aspects. First, we consider social, economical, and organizational aspects. Then we briefly explore the history of data and knowledge in computer science, trying to understand the relationship between these concepts. And together with this, we try to answer the question of why graphs have been so successful in representing data and knowledge. The answer to this question lead to several technical challenges. For example, the challenge of constructing a data model that is appropriate for some domain, the problem of integrating different graph, data management, querying, the problem of visualization, the problem of completion and refinement, how to add missing edges from a graph or to remove wrong edges from a graph, search and exploration, reasoning, in particular when you have an ontology, different aspects related to natural language processing, in particular how to extract information from a graph by using a query language that is based on natural language, different aspects relate to analytics, and how humans are part of these challenges. In this talk, we will focus on querying, in particular in what we call local queries. We have to do with the local structure of the graph, extracting nodes and edges from a graph, connectivity, which has to do with path and reasoning about them, and global properties, we have to do with properties of the entire graph. Obviously, querying has to do with data models. When you pose a query, you need to use a data model. So this is something that we will also consider in this talk. And we will also consider how humans are part of these challenges. We will conclude this talk with some takeaway messages, which are a summary of our reflection on this subject. So let's start with the first part of this tutorial, which will be given by Juan.
So why are we here? Why do we see graphs everywhere? Well, let's start with the obvious. We've all been hearing about knowledge graphs from all the big tech giants. Actually, knowledge graphs was a term popularized by Google with their things not strings approach. This was back in 2012, almost 10 years ago now. And this spawned a lot of interest from industry. So we also see a lot of other big tech giants like Amazon, right? Amazon is doing their product graph, and they're using knowledge graphs to improve search and recommendation and personal assistance. And many people from this community are at Amazon and making this possible. We also see Apple using and Siri using knowledge graphs for this. We see companies like Microsoft using knowledge graphs to be able to go integrate different types of their systems. There was a paper back in, I think 2 years ago in the ACM talking about industry knowledge graphs from Microsoft, Google, Facebook, eBay, and IBM. LinkedIn has their knowledge graphs. We can keep going. Netflix, we have all these big tech giants are talking about the knowledge graphs that they have. Now, another thing that is kind of obvious to this community is that there's large knowledge graphs, starting out with DBpedia, right? DBpedia was that structured version of Wikipedia, taking the info boxes and making that graph version of it. Yago has been around also for probably 10 years, creating a large knowledge graph from like Common Sense. We have Wikidata. Wikidata was the structured version of Wikipedia that I think has been around now for 5 years, and they've been growing and growing. We have Data Commons coming from the same group that's done scheme.org. That is an open knowledge repository that combines a lot of public data sets, in particular statistical information. And in the last couple of years in the United States, the NSF has been funding these open knowledge networks with the goal of to be able to go integrate in creating knowledge graphs that are integrating different domains. Now, another thing that we cannot avoid talking about is the obvious market growth that we're seeing within an industry. Graph databases are growing. If you go to the popular ranking of DB engines, we can see that graph databases are the fastest growing database, new types of databases out there. And in addition to seeing the growth of these systems, we can the pundits and the analysts are talking about them. And I'll take a bit of a academic scientific license here to go talk what showing what Gartner is saying. Gartner is saying that graphs are everywhere, and they're the number 8 trend in 2021 for data analytics. And specifically, in their latest management guide, the market guide, they're predicting that by 2025, graph technologies will be used in 80% of data analytics. Last year, it was only 10%. This is something we cannot deny. Graphs are everywhere, and they are in the real world. But we always hear about like the big tech giants and the graph databases, but there's also a large segment of the real world that are using graphs that may not be popularly known. Last month, Mohammed Oster, the chief data officer of McKinsey, gave a presentation at the Knowledge Graph conference and was giving examples of several companies that he talks about, that he knows about, that are using knowledge graphs. This is just a couple of them, right? BBC uses them to go power article recommendations. Electronic Arts has their intelligent content ecosystem where they're integrating all types of data for games. United Healthcare, one of the largest insurance companies, also use them to be able to go integrate data and claiming hundreds of millions of dollars in your savings, right? There are many, many more companies out there who are using knowledge graphs internally. They just may not make any public statements about that, but this is happening every day. Now, in addition to just companies who are using knowledge graphs internally, there's an entire segment category of data companies that companies who treat data as a product and they sell the data by themselves. And all these companies are powered using knowledge graphs and graph databases. Wunderman Thompson Data, now rebranded as Choreograph, has a knowledge graph for every single person in the United States. And they're now able to go do in 12 hours what they couldn't do in 6 minutes. These are actually case studies that they've presented. Reonomy has a large knowledge graph about real estate data. Diffbot is crawling the web and making a knowledge graph just like what Google does, but to letting people have access to it. Enigma is a company that sells private small and medium business data. All of these companies, and there are many, many more who treat data as a product, they're selling their data, and they're all part of creating this using knowledge graphs. Now, talk about a little bit history, just to kind of give you a quick glimpse about the history of knowledge graphs. Claudia Gutierrez and I have a paper in the Communications in the ACM magazine where we present this history of knowledge graphs. Now, the term knowledge graphs comes around 2012, but we go back to almost 50, 60 years looking at how this, all the different advancements that has happened. We categorize 5 areas at the beginning about how to represent knowledge in a graphical form, the quest to be able to go automate reasoning, searching in spaces, information retrieval of unstructured sources, and then language and systems for managed data. And from there, we see a lot of kind of the early advancements, the early results that we see, for example, semantic networks and A-star search and network databases. And what we see around this time, kind of in the 70s, is these 2 areas of computer science about knowledge and data. And they're their own communities who are starting to study knowledge and data as their object of study to understand how to manage it and how to go scale it. And over time, what we're seeing is how these 2 areas are starting to go integrate themselves. So in the 70s, we have things like conceptual graphs and frames. In the data side, we have relational algebra and ER and the first relational database management systems. The first workshop on logic and databases is that what tries to combine these 2 areas of logic and data. And it's particularly in this workshop, you have things like closed world assumption and negation as failure. In the 80s, you have description logics, right? You have the golden era of object-oriented databases, the Japanese 5th generation project that tries to create AI systems based on Prolog. The AI winter comes along, right by the end of the 80s and early 90s. And this spawns a lot of other work to think about methodologies on how to go create expert systems. The big thing that combines logic and data in the 90s is deductive databases and the start of data log. A lot of work on data integration happens because of the web. In the 2000s, we see the uprise of the semantic web with all these standards, but then big data becomes the big thing. MapReduce, Bigtable, which leads to all this NoSQL and graph databases. And this is just a very quick glimpse of what has happened, of all the different results that have happened in the last 50 years that has taken us to this quest of integrating knowledge and data at scale, to this thing that we're calling today knowledge graphs. So on a third aspect I want to talk about is, how is the academic community looking into knowledge graphs? So we did a very, very quick preliminary analysis, nothing very scientific, just to kind of understand a glimpse of what is going on. And we looked at all the data from DBLP, and we just looked at the titles of papers. And we looked at the titles of the papers in DBLP that have the word SPARQL, RDF, property graph, knowledge graph, and graph databases. Other means that there was a combination of these words. And what we can see is a steady increase of the quantity of papers being published about all these terms that we're connecting into knowledge graphs. What's interesting, as you can see, is that the blue, which means knowledge graph, starts to grow right after 2012. The orange, which is RDF, continues to be very stable. Just sharing here observations about this. Now, another thing that we were looking into is, where were these papers published and what venues? And we were looking at all these papers by semantic web venues, AI ML venues, database venues, and archive. Now, what we're seeing here is that, first of all, there's a very long tail, which is that top orange line that we're seeing. But if we take the long tail out, we see that there is a kind of a steady publications, higher publications in the semantic web community, not surprising. We see very flat kind of yellow, which is in the database community, which is the lowest. And what we see around 2017 is starting this increase on papers of these knowledge graph related papers being published in AI venues, and also kind of an increment in, on archive. So these three things that we just talked about. First of all, the real world. Knowledge graphs are not just for the tech giants. The tech giants started these, but they're in so many different places, and it's going to keep growing. Second, there's a rich history about knowledge graph. This isn't new. It's been boiling up for a while, and we are at the right time to be able to keep working on knowledge graphs. And third, there has been a steady academic interest about knowledge graphs. And with that, I'm going to pass it to my colleague Claudio, who's going to go talk about more of graph knowledge and all the mathematical structures and how all of this is combined.
Thanks, Juan. I will try to answer this question. What's new today? Graphs were long ago recognized as prime representation of media for knowledge. Also, the network characteristic of data was also known in the community of graph databases and computer science in general long ago. Finally, graphs as mathematical objects also were studied and known long ago, at least since the middle of the 20th century. So the novelty today really is the integration of these three streams, the three previously disjoint fields of research. This is what we know now as graph databases or knowledge graphs, or graphs I will put here in the middle. So there is a branch that deals with knowledge, with data, and with math. I will briefly try to review. Knowledge and graph has an old history, at least since Aristotle. And the shape visualization of the category of Aristotle is well represented here at the right. Here we have nodes very well defined and edges between nodes, a very primitive notion of graph. A more elaborate notion of graphs here, the nodes have a different type. Now it's text. Also, there are connections here between the leaves, and there are labels attached to edges. Also, there is an incorporation of an order, a notion of order inside the trees, inside the graphs, but we have here in these pictures a visual representation of the difficulties of dealing with these huge diagrams. Here we have another pair of pictures that represents, is kind of remind us XML in the 15th century. The order of nodes and the organization of knowledge inside a quipu in the Inca world. Different type of nodes, rounds, squares, and different organization of those nodes and different organization of graph structures here in this philosophical representation of Athanasius Kirchen of knowledge. Newton also used to use the graph as a representation for his, I mean, mental pictures. This is a conceptual graph by Wells. Look the difficulties here of trying to represent and to convey this idea of boxes of topics and relationship between those topics that are not as simple as represented by one edge or one line. It's more complex here. Below you can see that there is something more complex going on when the graphs and the complexity of knowledge grows. The chemical discipline also have this idea of graph representation of knowledge. And finally, in the 60s, social networks are kind of boiling down all this notion of diagrammatic representations with this very simple model of nodes graphs. Here we can see a representation of the Florentine families network by marriage between families. Peirce also, at the end of the 19th century, Schroeder too, with the algebra of logic, they were looking, or they were advancing the idea that diagrammatic representation is crucial for dealing with knowledge. And Peirce observed that in the diagram you can see things that passed unnoticed or hidden in the textual representation. This is very important. The same happened with this graphical representation of the syllogism of Aristotle. You can discover things that were not present previously in the sentence alone. And here, same thing, a textual representation, a textual expression, and a graphical representation above. And here, a very complex, this is Lukasiewicz notation of a formula, a logic formula. And here is Peirce's idea of how you can see what's going on below. I mean, this nested representation of sets that represent unary predicates. Semantic logic, semantic network really then join the worlds of knowledge/logic and data in a diagrammatic form. And so a diagram now is a representation of knowledge more explicitly, in the sense that you can derive sentences, or you can see in some sense sentences inside the diagram if you formalize a little bit the idea of the network. Why this unusual effectiveness of diagram to represent knowledge? First, there is a simple way of abstracting ideas by entities and relationships. Second, this is easy to visualize for humans. So, third, there is a simple way of operationalizing knowledge and communicating it. And finally, you can see things that you were not seeing before, as Peirce already noticed in his work at the end of the 19th century. So why graphs? Yeah, why graphs? So graph really became popular because it's an absolutely simple way of representing. It's the atomic way. The atom is composed of elements, simple elements, is diagrammatically ordered in the mind of physicists. Here we have the same. We have nodes and we have relationship between things, and those are the basic tools, yeah, the basic elements by which we can represent almost all knowledge that we have. This idea of graphs can be easily represented as mathematical model and then use all the power of mathematics to approach and to deal with them. Second, the human perception that is coded in these graphs can be extended and automatized. So we can put computers to work in our favor by dealing with this graph coded as data. And third, you can scale all these methods well beyond human capacities. So what's going on? Now we have graphs move to the realm of data and graphs. Yeah, we already saw the problems that we had. Complex diagrams are difficult to handle. Many particular data in metadata in the graphs were written in different forms. I mean, as text, with some, I mean, in some language, in some other language. So the interoperation of these different diagrams with different pictures, for example, those that you find in an encyclopedia, are really difficult to deal with. And then paper, of course, made the image static and difficult to handle. So the digital, what's the digital incorporates to this is the flexibility, the absolute flexibility to deal with this new type of data. So we have graphs, we have data, and we have the digital in the middle. We have then graph databases. This is the picture of a representation of graph databases in the 60s, yeah. And then in the 80s, after Code introduced this wonderful idea of the separation of concern of the logical from the physical, we got this what's called today golden era of database in the 80s. Yeah, here we have a diagram by Mendelssohn, and here in red the graph that has a lot of background from the mathematical logic, from knowledge representation, from graph theory, from semantics, from the rational model, and so on. So graph databases were a kind of a synthesis of all these trends. Why they didn't flourish? Because they flourished 2 decades afterwards here in this explosion, the red explosion below. Yeah, why they did not succeed? Because there were problems of hardware, of software, and visualization. You can see here the attempts of Consensus Mendelssohn in the 90s, and it's a very interesting idea. I mean, mathematically it's very well founded, but it's a mess. And we didn't have the good hardware and software to scale it at levels that we need. Why? Because we need millions of nodes and edges. Yeah? We also need versatile visualization software that we didn't have. And then we needed to incorporate, and now overall, we need to incorporate multimedia, that is images, sound, and video as nodes and the relationship between them. How to deal with that? In fact, we can see that this last part, this incorporation of multimedia, is one of the key trends that makes the jump, at least in name, from what is called graph databases to knowledge graphs. But essentially, we're talking about the same thing. I mean, the visualization of knowledge by means of graph data. What's preserved? The simplicity of the representation, nodes and links. That's the very essence, independent of if nodes are complicated, different type of edges, but nodes is very basic. And this idea makes very simple the integrate and possible the integration and the expansion, because it's just adding nodes, adding edges, and then it's just joining nodes and edges of the same type. This drove the field to this upheaval to graph databases and this explosion, yeah, and let's call big data, massive graphs, and all what we know today, and what's the object of our concern today. Here comes to the rescue mathematics. Okay. If at this point we joined, or we were aware of the joining of knowledge and data, okay, now we have to study, because we have knowledge and data, but a very large scale. And so graphs have to be studied in that very large scale. And for those, there are questions that, I mean, that comes to the field of everybody that wants to address the idea of managing, querying graphs. What are the basic structures of such large network? How do they evolve? What are the underlying principles that dictate their behavior? How are subgraphs related to the large host graph, and so on? Mathematics gives some fundamental tools, first classical tools from Erdős and Renyi, I mean, combinatorial and probabilistic method and spectral methods. And then when people realize that real life graphs have different distribution, I mean, more complex distribution than the normal one, general random graph theory, percolation theory that comes from physics, PageRank, and game theory, and so on. So we can round here and give a more holistic view of the field. So mathematical not only bring tools, but brings a way of conceptualizing things. And here the geometry of the local global is of help. How to deal with this, I mean, variety of properties that graphs have. Okay, first, graphs, I mean, very large graphs can be dealt with in a geometrical form. At the locally, we have nodes and we have edges and some small, very small neighborhoods. This is, I mean, a graph is a union, almost infinite union of these things, okay? So when you look at the union of those things as a whole, you have the global property of the graph, the emergent properties of joining all these pieces together. The idea of this piece together is the local, and in the middle, when you take two locals at certain distance, yeah, you have the notion of connectivity that links them together. That is a very, I mean, very interesting idea in graph theory that is introduced here. So we have these three big fields, and this gives a very nice, I mean, frame for studying how to address graphs, how to query graph, and that's what Marcelo is going to tell you in what follows.
In this part of the tutorial, we will try to answer the questions of what are new challenges and what are new techniques. You should keep in mind that we are not trying to provide an exhaustive list. We are just trying to identify new challenges and techniques that could be of interest for the database community. So as Claudio mentioned in the previous part of the tutorial, we will consider local properties, connectivity properties, and global properties. In the case of local properties, which have to do with the local structure of the graph, we will consider the old problem of extracting nodes from a graph, but we will mention a recently established connection between first-order logic and graph neural networks. In the case of connectivity properties, which have to do with path and reasoning about them, we will consider the problem of uniformly generating them, and we will also briefly mention this idea of having path as first-class citizens in query languages. And finally, in the case of global properties, which have to do with the entire structure of a graph, we will consider the problem of explainable AI and the search of declarative language for interpretability. So let me start by considering this whole problem of extracting nodes from a graph. In our running examples, we will use notation n sub I to represent node identifiers. For example, in this case, we're saying that n3 is a node identifier. We use notation e sub I for edge identifiers. For example, we are saying that in this case that E2, it's it's an edge identifier. We have nodes with labels infected, pass, person, and company. And we have edges with labels writes, friend of, and works at. And we use these labels to represent different relationships between nodes. So for example, we can say that, in this case, we're saying that N1 is a person who is a friend of a person N2. We're saying that N2 is a person who works at N4, which is which has labeled company. So N4 is an identifier for a company. And we can also say here that a person rides a bus. So in this case, we are saying that N5 rides the bus with identifier N6. In our running example, we are trying to we are defining different notions of close contact for an infection disease, and we are trying to identify people who could be at risk. So, for example, in the case of this regular expression, what we are doing is the following. And let me introduce the notation also for regular expression. We use a question mark the question mark here to indicate that we are looking for a node with a label, in this case with label person. We are using, in this case, the labeled rights without the question mark to indicate that rights is the label for an edge. And well, in this case, we are using again the question mark to indicate that bus is the label for a node. And so in the first part of this regular expression, what we are saying is that we are looking for a person who is connected with the bus by means of an edge with label rights. And we also use here this usual notation minus to indicate that we have to traverse an edge in the opposite direction. So what we are saying here is that we are looking for a bus who is connected with the node with label infected by means of an edge with labeled rights. But we are also saying that we have to traverse this edge in the opposite direction. So here in yellow, we are showing a path that satisfies this regular expression. And what we are saying is that, well, person is connected with bus by means of this edge with label rights. So this is the first part of this regular expression. And then we are saying that bus is connected with the node with label infected by means of an edge with labels rights. But we are saying that we have to traverse this edge in the opposite direction. So let me also consider an old idea in the database area, which is the idea of using Perceval logic as a query language. In this case, we use binary relations to store nodes and the labels of these nodes. So for example, person, it's a unary relation. And we use, when we say that X belongs to this unary relation, we're saying that X is a node with label person. We use binary relations to represent edges. In this case, we're saying that we use rights in this case, which is a binary relation to represent edges with label rights. So in this particular case, we're saying that X and Y are nodes which are connected by means of an edge with label rights. And then we use the different connectives and quantifiers to construct a query. So in this particular case, we are saying that X should be of type person, and this X should be connected with some Y. So that's why we have an existential quantifier here by means of an edge with label rise. We are saying that this Y should be of type pass, and then we are saying that there should exist a set which should be connected with Y by means of an edge with label rise, and that the label of this set should be infected. Yeah. So this query represents the regular expression in the previous slide. So finally, let me also consider an old idea in the area, which is use first-order logic with bounded resources. By bounded resources, in this case, I mean use a bounded number of variables. So notice that in the previous query, we use 3 variables, x, y, and z. But notice that this set here, actually, the only thing that we are saying about this variable is that it should be connected with y, and it should be, the label of this set should be infected. So we are not establishing any connection with x, and actually this means that we could reuse x in this case. So it doesn't make any difference in this case whether this quantifiers is there exists a set or there exists an x. And if we use the quantifier there exists an x, we are not creating any confusion with this variable x here, that in yellow, which is the variable that we are trying to return by using this query. So why is this useful? Well, if only 2 variables are needed, or if a bounded number of variables are needed, then well, only the values of these variables need to be stored. That's something important, because then we don't need to store partial results from joins of arbitrary size. Actually, what we know in this case is that the joins that we are going to compute are always, or the intermediate tables are always going to be binary tables. So let me show you this in an example. So in this case, we have the previous query where we reuse the variable x. Notice that what we have here is the different tables, which are the answers for the different atomic queries that we have here. So for example, person X, and here we have the answer, and we explicitly mention the variable that is used in this atomic query. So why I'm showing this? Because this will give us a simple way to answer this query, and the idea is the following. So initially, what we have to compute is the result for this query infected X, which is shown in this table. The result for rights of XY. Again, here we have the different tuples that belong to the answer to this atomic query. And then what we have to do is to compute the join, in this case, on the variable X. And we will obtain as a result this tuple and 0 and 3. Once we have done this, we need to do the projection, and in this case, just keep the value of the variable y. And notice that once we have done this, we realize that the variable x was really not needed, actually. So we just need the value of the variable y, which in this case is going to be used to restrict, the rest of the query. So what we have to do here is to compute the join between this query, this atomic query pass of y, and the result that we just computed, and we will obtain this result in 3. Then again, we have to do the join, in this case, on the variable y, and we will obtain this table here with tuples and 0 and 3 and 1 and 3. Finally, well, we'd say that we have to compute this projection, and we just have to keep the value of variable x, and we will have this table here, and we can compute the result of the query just by doing the join on the variable x, and we will obtain this. So as you can see, the important message here is that you just need to store binary tables, because you just need to store the values of variables x and y. So on the other side, let me talk a bit about graph neural network. Graph neural network have been widely used in the machine learning community, and the main idea behind this neural network is to have an architecture that can take into account the structure of a graph, right? So, for example, in this case, and again, thinking about the previous example, what we want to do is to find people who is at risk, and in this case, well, there is a notion of close contact, which is this idea that the person rode the bus, and this bus was ridden also by an infected person. right? So, what I'm going to show you in the next slide is how such a query can be computed by the graph neural network. So you can think of a graph neural network as a neural network that has as input a graph, and which has as output a classification for each node of the graph, right? So you can think of the results of this graph neural network as the same graph, but where each node has a label 0 or 1, right? So, and this means that when you have the output, each node has a classification, right? You have classified this node either as 0 or 1. So, so in order to do this, we need to consider a different data model from the previous one, and this is something that you can find in the accompanying paper for our tutorial. The idea here is that you will continue using identifiers for nodes and edges, but instead of having labels for nodes and edges, you will have theater vectors for nodes and edges. So instead of just associating a label to N0, like what we were doing before, now we want to associate a vector of theaters. And well, in this particular case, we are just associating a vector of dimension 1. So this is a representation of the previous label graph. So what we are saying here is that the label of N0 is infected and the label of N3 is Baz. But actually, you could have vectors with a larger number of theaters, and this will be the dimensions of the vectors that we are using. In particular, for our previous task, which is finding people who is at risk, we are going to consider now vectors of dimension 2. So initially, you can think of the vector associated to N0 as an infected 0. So we use the first element of this vector to represent the label of this node, and the second theater of this vector to represent the classification. So the idea of this graph neural network is that it's going to process the graph, and eventually it's going to change these vectors of theaters. And the way this graph neural network works is as follows. So the idea here is that, and this will be computed by layers actually. So you will have a number of layers that is specified in the graph neural network. The idea is that to process the and each node, what you have to consider is what is the current vector of theaters of that node, and what are the vectors of theaters of the neighbors of that node. So in this case, we are saying we have N3. N3 is of type Baz and has value 0 in the second value, and the neighbors of this node N3 and are N0 and N1, and these nodes have these vectors of theaters. Well, the graph neural network takes into consideration then the vector of theaters of the node and a multiset with the vectors of theaters of the neighbors of that node. And why a multiset? Because they could be some repeated vectors, and the idea is that you should keep, or you should, if you have repeated vectors, you should know that actually. So the idea here is in this case, actually, if we are thinking about our previous example, what we want to identify in this first layer is what are the bases where infected or that infected people wrote. So in this case, for example, what we are saying is, well, this is a Baz, and there is an infected person who wrote that Baz. So what we would like to have as the result of this first layer is that the new vector of theaters of this node is Baz 1, right? So we have changed the value of the second value given that actually that bus was ridden by an infected person. And then we will continue in the same way, actually computing the result for this graph. And in the second layer, what we want to do, again, always what we are doing when we are processing a node is to consider its vector of theaters and the vector of theaters of its neighbors. So in this case, we have N1, which has this vector of theaters, is a person with label 0 in the as its second value, and second value of the vector of theaters, and in its the neighbors of this nodes have vectors of theater bus 1 and bus 0. And notice here again that well, in this case we have two different vectors, so the computation depends on this the vectors that we have here. But again, if we have repeated vectors, we should keep the copies. I mean each copy for these repeated vectors. So in this case, what we're trying to do in this layer is to say that, well, if a person wrote a bus which has value 1 in the second theater, then that person is at risk, because we know that this value 1 indicates that an infected person wrote that bus. So the result of this layer will be a person, in this case, for the node N1, and we have to do this for each node. The result then will be a vector of theater that has value person in its first component and value 1 in its second component. So then the computation will continue in this way for a fixed number of layers. And actually here we can define in a more precise way what is the architecture of graph neural networks. What we have, it's a vector U, which is the vector of theater of node U at layer I. What we call U sub 0 in this case then is the vector of theater from the input graph. So at the beginning, for each node U, we will have a vector of theater U sub 0. In the layer I, we'll have a vector of theater U sub I. And how do you compute this vector of theaters? Well, in the layer I+1, the way to compute this is exactly as we described before. What you have to do is you have to consider all these which are neighbors of U in G. You have to consider the vectors of theaters of these neighbors, what we call at layer I. So this is what we call V I. And then you have to apply some aggregate function. And notice that here we're using the multi-set notation because we will keep the duplicates, and you define an aggregate function, which could be a function, for example, that could be a linear function, for example. I mean, there are different ways to define this, but the idea is that you take all these vectors of theaters from the neighbors and you compute this aggregate function. And finally, you combine this with the vectors of theaters of node U at layer I. And you compute with this actually the new vectors of theaters for this node U, in this case at layer I+1. And finally, when you define this architecture, if you have k layers, then you have to say at the end, actually, so once you have computed the layer k and you have this vector uk, right, which is the vector of theaters in the last layer for each node, you have a classification function, right, which is going to say what should be the result. So for example, in our previous example, assume that we have 2 layers, so we are representing this regular expression in our running example. So once we finish processing this graph, what we obtain is these vectors of theaters. So for example, for N3, we obtain the vector of theater bus 1. And the idea here is that the classification function, what it says is that you have to take each vector of theaters And what you are saying is that what we have to classify as one is the vectors of the form person one. So because we are looking for these people who is at risk. So what we're saying is that in the first component, we should have person, and in the second component, we should have value one. So the nodes whose vector of theaters it's of this form, person one, this will be classified as one. And all the other vectors of theaters, in particular person zero or infected zero, infected one, bus zero, 1, 1, all the others will be classified as zero. So in this case, the only node that will be classified as one is N1, which is exactly, and the rest will be classified as zero, which is exactly the same answer that you obtain by using this regular expression and the first order query that I showed you in the previous slides. So the idea here is that the question is, how are the previous paradigms related, right? What I show you is an example, right, of a regular expression and then a graph neural network that computed exactly the same answer, right? When we are thinking of a graph neural network as a query, right? And the interesting idea, and this is a new idea, is that there is a graph isomorphism test that has been used for a while, actually, which is this Westphiler-Lehmann test that actually established the connection between these two paradigms. And actually, this tells you actually that there are two alternative points of view. I mean, first of the logic is a declarative language with a well-known studied inference mechanism. On the one side, it establishes this connection, and on the other side, graph neural networks are a popular classification paradigm with a growing number of algorithms and techniques to learn and implement them. So we have, if we establish a connection between these two paradigms, actually, we can take advantage of these characteristics of these models. So, and how is this established? And let me show you this Westphiler-Lehmann test. I mean, just by means of an example, because you will realize that this is quite close actually to the notion of a graph neural network actually. So what we are going to construct is just for this graph here, we will see how is the computation of this Westphiler-Lehmann test and for the one-dimensional test. So the idea here is very simple. So the idea is that initially you assign the same color to all the nodes. In this case, all nodes are colored with number 1. And then you start exactly in the same way as you do for graph neural networks. You start looking at the neighborhood of a node, and you use that to assign new colors to the different nodes. Essentially, what you are saying is that, well, you have to see, I mean, for example, how many neighbors a node has, and then you will have, if a node has 2 neighbors and another node has 3 neighbors, then you should say that these nodes are of different types, right? They have different numbers of connections. And again, you can do this recursively, and you can say, well, if this node is connected with a node of this type, and that node is connected with a node of different type, then you should say that these nodes are different. This is essentially the idea behind this Westphiler-Lehmann test. So let me show you how it works. Essentially, the idea here is that you compute the type in the same way that you do for graph neural network for each node. For example, in this case, you are saying the color of this node is 1. And here you use a multiset to indicate that what you have as neighbors are 2 nodes with number 1, right? And you do that for every node. So for example, in this case, you say for this node, the color is 1, and I have 3 neighbors with number 1. So once you have finished with that, you say, okay, let's use new colors to distinguish these types. And in this case, we have 2 types, right? We are saying we have one type, which is 1, with 2 neighbors with label 1 or of type 1, and we have 1 with 3 neighbors with label 1. So we assign new colors. Let's assume that, let's say that there are 2 and 3, and notice that at this point we can distinguish between this node here and the nodes that we have here. And the test continues like this, and again you do the same computation. You say, well, here we have a node with number 2 or color 2, which is connected with 2 nodes with number 3. You say here we have a node with number 3, which has 2 colors, which is connected, sorry, with 2 nodes of type with type 2 or with color 2 and 1 node of type 3. And we do this for the node here, and we say, well, the color of this node is 2, and is connected with a node with color 3 and with a node of color 2. And notice that what is interesting here is that now you have to assign colors again, and you will be able to distinguish between this node here on the top and this node on the bottom, right? Because they have been assigned different representations, right? So you will do this new coloring. And again, you will do the same, and you will say, well, here we have 4, which is connected with 2 nodes with numbers 5, and here we have 5, which is connected with 4, 5, and 6, 4, 5, and 6, and here we have 6, which is connected with nodes with number 5 and 6. And notice that in this case, when you have to assign colors again, and you will say, well, we need a color for this node on the top, we need colors for these nodes with number 6, and we need a color for nodes with number 5, and we reach a fixed point, actually. Fixed points in the sense that we have not changed the colors. And what you get as the representation of this graph are this color. Essentially, what you are saying here is, well, we have a node of type yellow, which is a node which is connected with 2 nodes of certain type, actually. And you have 2 nodes with this color, and you have 2 nodes with this color here on the bottom, right? So this is, I mean, if you think about it, actually, this is quite similar to what you do in a graph neural network. So, and the idea here is that the Westphal-Lehmann test can be considered as a heuristic to verify whether 2 graphs are isomorphic. I mean, it's not, I mean, it's a polynomial time algorithm, right? But there are no polynomial times or not known polynomial times for graph isomorphism. This is heuristic. What we know is that it could be the case that 2 graphs are isomorphic, but once you compute their types, actually they look exactly the same. But it's a very good heuristic. It allows us to distinguish between many graphs that are not isomorphic, and we have theoretical guarantees. But what is interesting in this case, actually, is that really this is the bridge between declarative query language in graph databases and graph neural network used in machine learning. In particular, this is a result from 2019, and what this result says is that, well, that if this Westphal-Lehmann test assign the same color to U and B in a graph, then every graph neural network, which is what we mentioned here, is an aggregate combine, which is the architecture that I just showed you. I mean, with the aggregate and combine function, classifies U and B in the same way on input G, right? And this result is used to establish this connection. And why is the reason? Because also, I mean, it was known from a result from 1992 that this Westphal-Lehmann test is connected with first-order logic, and is connected with first-order logic or with a fragment of first-order logic that is related what we saw before. And I use this notation. I mean, the details are really not that important, but the notation here, FOC2, 2 means that when you are using just 2 variables, exactly as we saw before. So the query that we saw before is in this fragment. We are using reusing the variable x in this case. And the 2 means that you can use quantifiers that can be expressed in first-order logic, but quantifiers of this form. I mean, something like there exists at least 2y, or you can say there exists at least 10y. What you are saying is there are at least 10 witness or 2 witness, right? And notice that you use this particular notation because if you want to represent something like there exists 3 y such that something, you need to use 3 variables to do that. So in this case, you are just using 1 variable to do that, right? And FOC2, the interesting thing, I mean, from the database point of view, is that it can be evaluated efficiently as shown before, right? I mean, with this idea of just using binary tables. So, and as I was saying before, and here is the formal statement, but essentially what was proved in 1992 is that this Westphalian-Lemon test assigned the same color to U and B in a graph, if and only if these two nodes, I mean, cannot be distinguished in this logic. And this gives you, and this is a result from 2020, is that there exists a natural fragment of this FOC2 that has exactly the same power as aggregate combined graph neural networks. And all the previous queries that I show you are in this fragment. And actually, it's a fragment that essentially say that you need to have a connected path, right? We are using writes in this case to do the connection. So, I mean, and why this is interesting, and here are just questions. I mean, you have, we just show you a result that says that two different formalisms have exactly the same expressive power, right? So what is interesting is that they offer or they have different characteristics, right? So what are the interesting queries here is that can learning techniques for graph neural network be used for learning queries on graph? Given that, I mean, these things have exactly the same expressive power, and what are good algorithms for translating aggregate combined graph neural network into well-studied declarative query language? And another question that is interesting, or that we think that is interesting, is what is the appropriate graph neural network architecture for regular expression? Notice that what I showed you before, or the example before, didn't contain the clean star, which is something that you cannot express in first order logic. So if you are thinking about what is the right query language and what is the right architecture for graph neural networks to represent regular expressions, then you need some form of recursion. So let me mention the old problem of extracting path from a graph. So what we have here is the canonical example of a regular expression that is used to extracting friend-off path from a graph. But in the case of our running example, we would like to also extract paths that represent a notion of close contact, which can be path of arbitrary length if we want to consider a stricter notion. I mean, something that is important here is that when you are looking for the path that connects to nodes, you can have a large number. So you could be more interested in returning not the set of, I mean, all paths, but in returning, for example, the number of paths that you have between these two nodes of a certain length, or in returning a representative path between these two nodes. So in that sense, you could consider problems like count of GRN. So in this case, G is a graph, R is a regular expression, and N is a length. And you are saying, well, I would like to return the path in the graph G that conform to R and R of length N. And in the same way, you can consider the problem of generating, in this case, generating a path that conforms to R and which is of length N. So are these difficult problems? Well, if we don't consider regular expression, this problem can be solved in polynomial time. This is very well known. But if we consider regular expression, these problems are shared P complete, which means that they cannot be solved in polynomial time unless P is equal to P. So how do we solve these problems? Well, we can give up precision. We can say, well, we don't want to compute exactly the number, but we want to compute an approximation. And here, actually, approximations are useful, in particular randomized approximations. So what we are looking for here is for an algorithm A that, given a graph, a regular expression, a length N and a relative error epsilon, right? Approximate this value count of GRN. And something that is very important is that this algorithm should run in time polynomial in the size of G, in the size of R, N, and 1 divided by epsilon. And if this is the case, that's what we call a fully polynomial time randomized, we say that the algorithm is fully polynomial, right? So, but something that is also important here is that randomization is needed. And what I'm saying here is the following. What we have in this expression here in yellow is the relative error of this algorithm, right? And what we would like to have is that this relative is at most epsilon. But what we are saying here is that the probability that this error is at most epsilon must be very large, right? In this case, we're saying that this probability should be at least 1 minus 1 divided by 2 to the 100. Essentially, we're saying that is 1. And again, we are asking for A to run in time polynomial in the size of the input, G, R, N, and in 1 divided by epsilon, where epsilon is the relative error. If we have an algorithm that satisfies this property, we say that this is a fully polynomial time randomized approximation. And in a result obtained in 2019, we showed that there exists a fully polynomial time randomized approximation scheme for count, which means that we can approximate this value. And something that I would say it's even more interesting is that it can be used to provide a randomized algorithm for the generation of a path. So samples can be generated efficiently with an almost uniform distribution. And let me show you an application of these results actually for global properties. So the question here is, how important is a bus service? And this question, in this case, we are formulating this as a question over the graph. And what we are doing essentially is we are trying to measure the centrality of these bus services. When we try to measure the centrality, we use a centrality measure actually, and one of the most popular is between centrality, which is defined in the following way. We say that for two nodes A and B, S is the set of shortest path from A to B in G, and we say that S of ABU is the set of path in the set SAB that include node U. So essentially what we're saying is we're looking for the set of shortest path from A to B that goes through this node U. And then the between the centrality of this node U is defined as, well, we do the summation for every pair of distinct nodes AB, such that, well, A and B are different from U, of this value here. And this value here essentially says, well, what is the ratio of shortest path from A to B that goes through U? And something important here is that between the centrality can be computed in polynomial time. But then something to consider is, well, that not all shortest paths actually are relevant when you are measuring the centrality of a node, in particular if you have a label graph, right? So for example, if you're trying to measure how important is a path service in the spread of an infection disease actually, so obviously a path that is connected the bus with the company because the company owns the bus is not important for this question, but a path like the one that is shown in this this slide actually it's important, right? Because this path represents a person who rode the bus, and that bus was ridden by an infected person, right? So how can you filter, or how can you specify what are the important paths for a centrality measure? Well, there is an obvious way to do this, which is by using regular expression. You can define again between a centrality, but in this case by saying we are going to consider the shortest path from A to B, but that conforms to a regular expression R. And again, you can say, well, then let's define this S of ABRU as a set of shortest path from A to B that conform to R, and that goes through the node U. And once you have that, you define the between a centrality exactly in the same way as before, by considering the path that conform to R. Then the natural question then is, well, can this notion of centrality be computed in polynomial time? Unfortunately, it cannot be done, right? Because you have regular expression, counting becomes difficult. But the good news is, again, that randomized approximation can help us here. In particular, the previous algorithm can be used actually with, if you want to obtain an approximation with error epsilon. So let me briefly mention this idea that a path should be treated as first-class citizens, and in particular, this also, and this is the second thing that is mentioned in this slide, this is also coming from this idea of how to measure the centrality of a node. If you think about this actually, so if you want to formulate this as a query, what you need to specify first are what are the paths that you should consider, and this should be done by using a query that specifies path that satisfies some regular expression. So essentially the answer to a query, which is a set of paths, should be used at the input of the following query, right? So what we would like to do in that sense is to use or to treat path in the same level as node and edges, in the sense that it can be stored and can be materialized. You can generate views that consist of set of paths. And if you want to do that, actually, it makes sense to have labels for them. It makes sense to have values for properties or even associated vectorial theaters like in graph neural networks. And here we have an example. Here we have in yellow a path actually, and you can think of assigning an identifier for this path like B0 and even a label, like in this case, infection route. So, I mean, some questions to think about actually. Can the previous randomized schema for count be effectively used in practice? And I think more importantly, it can be used to provide fair answers in practice, and given that it can be used to generate uniformly at random path that satisfies some regular expression. And what I think is very important is how can centrality measures be adapted to deal with graph databases and knowledge graph? And in particular, the question of what is an appropriate definition of a centrality measure that takes labels into account. It's a question that need to be answered, right? And how can paths be included as first-class citizens in a query language? This is, we think, is also an important question. Let me finish by going a step beyond and considering global properties and explainable AI. In this slide, you can see a label graph as the one that we saw before, where we use X, Y, 0, and 1 as node labels, and we use 0 and 1 as edge labels. You may be thinking that this is a strange graph, but actually if you remove node and edge identifiers, you will notice that this graph represents a classifier. In particular, if we follow this path here, we are saying that if you assign value 0 to variable X and value 1 to variable Y, then you will obtain 1 as a result of the classification. So we can represent classifiers in a natural way by using a label graph, and then we can answer some interesting queries and queries that represent questions that people would like to answer when they are trying to understand what a classifier does. For example, is there any instant that is classified positively, which in this case is represented by this yellow path? So again, we are reasoning about path, and the answer to this question represents a path where you have some values assigned to X and Y in a way that, in such a way that you end in a node with label 1. So for example, if you assign value 0 to X and then value 1 to Y, then you end in a node with label 1. Is there any instant that is classified negatively? Again, we have to reason about path. Is there a completion of the assignment X goes to 1 that is classified positively? In this case, what you are saying is that I have assigned value 1 to X, and now I would like to know whether there is any value that I can assign to Y that ends in a node with label 1. So for example, in this case, you can assign value 0 to Y, and you will end in a node with label 1. And you can pose other queries that are of interest for people that is trying to understand how a classifier works. For example, are all the completions of the assignment X goes to 1 classified positively? So what you are saying is that if we assign value 1 to X, then is it true that no matter what value assigned to Y, I will obtain 1 as the value of the classification process? So essentially what you're saying is that X goes to 1 is a sufficient reason for the positive value, right? No matter what value I assign to Y, I will obtain the same classification. And you can post more complicated queries that are of interest for people trying to understand how a model works. For example, given an instant classified positively, what is a sufficient reason for it? Like in the previous example, we could discover that, for example, if you assign value 1 to x, this is enough to obtain a positive classification, no matter what value you assign to y. What is a minimal sufficient reason for this instance? Or is the model biased with respect to a protected feature? So some questions to think about. How can a declarative language for model interpretability be defined? So the idea here is that we would like to define a declarative language where all the previous queries can be expressed, and we can express other queries that are also for interest or are also interesting for people that is trying to understand how a model works. And can such a language be based on path expression? Like in the previous example, we had to reason about some path. And how can such expression be combined with quantifiers? Actually, when we were thinking whether something is a sufficient reason, we have to use a universal quantifier. So we were saying, once we have assigned value 1 to x, then for every value of y, we will obtain a positive classification. And finally, can such a language be evaluated efficiently? And this is a very interesting question for our community, because this really depends on the structure of the underlying graph. And this is something that we have considered many times in our community, and whether we can evaluate a query efficiently depending on what is the structure of this of the graph. So this concludes this part of the tutorial, and Juan will talk now about how humans are part of all these challenges.
So up to now, we have gone through all these technical challenges. So we ask ourselves, is that it? Should we just be focusing on these technical challenges? Well, we have not touched a lot of other topics. These are just a handful of ones that we're aware of, right? Visualizations, having humans and visualizations of graphs. There's actually an upcoming doctoral seminar. Hopefully it's going to take place in person next January. There's the all HCI meets graph databases and graph query languages. We haven't even touched anything about storing and infrastructures of graphs. But then we actually have to go look at what's being done in the real world, in the enterprise, and what are the open problems over there, which additional problems are about governance and ethical issues. So the message here is that querying knowledge graphs and graph databases, this isn't just a formal or technical topic. It involves a lot of other aspects, and we are just scratching the surface here. An important reminder is that with the popularity and this interest right now of humans in the loop, is that humans have always been in the loop. Now, if we look at this context, right, we have the web and Moore's law. There's this trend of big data, and the needs in organizations were that they needed to go harness and collect all of this big data that was occurring. So what happened with the technology is that all these commodity distributed platforms came around, right? Hadoop, it became a commodity. Now, this was the context. This is the technology came out. Now, the role, the people that we see within organizations are the data engineers. We saw the rise of the data engineers in the late 2000s. And from there, big data grew. And we have all this great computation, so much computation, the GPU, and we started the AI revolution. Why? Because we finally had a lot of data, and we had the technology, commodity computing platforms to be able to go do stuff with all that big data. And that's where we see all of this machine learning being commoditized, right? TensorFlow and all these things came out. And what did that enable is this new role that we now take for granted, which is the data scientist, which is actually just became a thing around early 2010s. So now what we're seeing is this AI revolution and everything being the cloud. And all organizations are thinking about being data driven, and they have to have the digital transformation. And now the need is that, wait, we can already collect and manage data. We already need to go extract value out of all that data, but we still are not there on how we can rely on the data. How much can we trust the data? And the technologies that we're seeing right now are about how to be able to go manage all this data at a large scale. I'm seeing all these data wrangling tools and systems, these data catalogs, and now knowledge graphs. So the question is, what is that next role? Our position is that this next role is what we're calling the knowledge scientist, which can be seen, frankly, as the knowledge engineer 2.0. If we go back to history, remember, this was the roles of that happened in the early 90s around expert systems. I think we're going to receive this role again. Now, the question is, how is this role going to fit with all these other technologies and within the organization and with other people? If you want to see more about this, we invite you to go take a look at knowledgescientist.org. Now, it's important that we're talking about people is that data is a team sport. Now we're talking about data engineers, data scientists. We're talking about knowledge scientists. How are all these roles and these people going to be working together, right? This is what we need to start thinking about within the community. Additionally, the most important thing about data isn't the data itself. We really need to start thinking about how these people, and we're going to start documenting data, right? We're not such a big fan. We don't get excited about documenting data, but actually the most important thing isn't about data, but it's actually the code that generates the data and how we go manage this, right? Thinking about provenance and lineage. These are the important things that we're seeing coming next. Now, if we do this analogy with software engineering and software development, they're all agile methodologies around to develop software. We need to be able to bring these things into data and how to go manage data. And finally, we peer review papers, we peer review code. We need to peer review the data. So if we think about this, there's all these different aspects that are going to take data to the next level. And the data management community are at the center and be able can think about all the ways of how we can combine people, the processes, and the technology. Here's an example. For example, we've worked on this methodology to be able to go create these knowledge graphs in an iterative approach. And you have these, what you really want to think about is how to define success. How do I know that I'm actually generating data that's actually being useful and meaningful that people can actually rely on? So within organizations, you can say, well, there's sort of business questions that need to be answered. There's a first phase about understanding and capturing the knowledge within that, and want to be able to generate reports about what has been learned and have this peer reviewed. And then you can really take that report and go implement this knowledge and go implement that in the forms of ontologies and create mappings and generate data. And this can be validated. And this is when you're going to go see those enterprise knowledge graphs coming around. And then from there, you can actually take that and start actually building those reports or starting sending this data to your data scientists so they can actually they can rely on that data and start answering those questions. So if you're able to go answer that question, that's how you know you're being successful in this iterative approach. Next question comes along, you only need to understand, extend the knowledge graph with respect to that new question. And you do this in an iterative approach. That way you don't have to go boil the ocean. The point here is that we need to start thinking more about how we need to combine people and technology together. And this is where the processes comes in and thinking about methodologies. Here we have references for everybody to look at, which all these slides will be available right after the talk. So, takeaways. If there's one thing we want you to remember, is that graphs are not just another data model. This isn't something that has just become popular in the last 10 years. Graphs have always been here, and they are not going away. They have, even though the relational model really took over the world in the 70s, 80s, the graphs have always been there, always been there. They've come and gone, So they're never going to go away. But we believe this is the right time. We are really lucky to be here in this moment to think about how we can really take advantage of graphs and everything that we have learned over the last 50, 60 years. And knowledge graphs are more than just graph databases. This is thinking about how to go integrate knowledge and data at scale. And in this tutorial, we are just scratching the surface. It's very exciting to see results from different areas getting connected, as we talked about the connection between graph neural networks and graph query languages. And there's these huge opportunities. For example, how we can combine a declarative language for interpretability, and how that can be used to go be able to achieve explainable AI. Finally, computing is just approaching this fine line that separates technology from humans. And this is a call for arms on all of us to really reach out and go learn from other disciplines. We can't expect the other disciplines from social sciences, from HCI to come to us. We really need to take that bold step and go out and explain what we're doing, how we see the world, and see how we can go work together. And with that, thank you very much.